we will see the solution of set 6 questions. Consider a semiconductor which perfectly validates the Hazel relation at all temperature. It is also given that the relation of band gap energy with temperature is linear with value 1.14 electron volt at 150 Kelvin. Let us first write this data. It says that band gap energy at 150 Kelvin is equal to 1.14 electron volt. And if we plot the relation, then the line will be parallel to a standard linear relation of band gap energy with temperature for silicon. You know that the band gap energy relation for silicon with temperature is 1.21 minus 3.6 into 10 to the power minus 4 multiplied by temperature in Kelvin. It is given that the band gap energy function of the semiconductor is also linear, meaning that we can write it in the form of A plus BT. It is given that if we plot the relation, then the line will be parallel. It means if this is the line of silicon, then the semiconductor line is also parallel, meaning that the slope will be equal. And the coefficient of temperature is the slope of the function. It means we can write the band gap energy of semiconductor to be equal to A minus 3.6 into 10 to the power minus 4 multiplied by temperature in Kelvin. It is also provided that at T is equal to 150 Kelvin, band gap energy is equal to 1.14 electron volt. It means that 1.14 electron volt A minus 3.6 into 10 to the power minus 4 multiplied by 150. And after solving the equation, we will get the value of A to be equal to around 1.194, which gives the relation of band gap energy of the semiconductor with temperature to be equal to 1.194 minus 3.6 multiplied by 10 to the power minus 4 multiplied by temperature, where temperature is in Kelvin. Now the question is, if transverse effective mass at 150 Kelvin is equal to 1.56 m naught, then what will be the value of transverse effective mass at 300 Kelvin? It is provided in the beginning of the question itself that the semiconductor follows Hazel relation at all temperatures. And as per the Hazel relation, we have transverse effective mass at 150 Kelvin multiplied by square of band gap energy at 150 Kelvin equal to transverse effective mass at 300 Kelvin multiplied by square of band gap energy at 300 Kelvin, which gives transverse effective mass at 300 Kelvin to be equal to transverse effective mass at 150 Kelvin multiplied by square of band gap energy at 150 Kelvin divided by square of band gap energy at 300 Kelvin. Now we have transverse effective mass at 150 Kelvin, we have band gap energy at 150 Kelvin, and we have already found the equation of band gap energy of the semiconductor with temperature. Now putting the value of T equal to 300 in this equation, the value of band gap energy at 300 Kelvin will come approximately equal to around 1.086 electron volt. Transverse effective mass at 300 Kelvin will be equal to 1.56 m naught multiplied by 1.14 divided by 1.086 raised to the power 2, which will come approximately equal to 1.72 m naught. So, the transverse effective mass at 300 Kelvin will be approximately equal to 1.72 m naught. In a non-degenerate bulk semiconductor with hole density P is equal to 10 raised to the power 16 per centimeter cube, the value of EC minus EFP is given to be equal to 200 millielectron volt. Assume thermal voltage as 26 millielectron volt and the intrinsic carrier concentration is 10 raised to the power 10 per centimeter cube. For P equal to 0.5 multiplied by 10 to the power 16 per centimeter cube, the value of EC minus EFV will be case 1, in which P1 is given to be equal to 10 to the power 16 per centimeter cube and EC minus EFP1 is given in the question to be equal to 200 millielectron volt. Similarly, we have case 2, in which P2 is already given to be 0.5 multiplied by 10 to the power 16 per centimeter cube and EC minus EFP2 is asked. We have a formula according to which Fermi energy level EF minus valence band energy level EV is equal to kT multiplied by natural logarithm NV divided by P, where NV is the effective density of states in the valence band and P is the hole concentration. Now for case 1, we have EFP1 minus EV is equal to kT natural logarithm of NV divided by P1. Let this equation be first equation. Similarly, for case 2, we have EFP2 minus EV equal to kT natural logarithm of NV divided by P2. Let this be second equation. Now, after subtracting second equation from first equation, we will get EFP1 minus EV minus EFP2 minus EV equal to kT natural logarithm of P2 divided by P1. Now, if you draw the band gap diagram, this will be EC, this will be EF and this will be EV. And also you know that band gap energy is equal to EC minus EV. Band gap energy is also EC minus EF plus EF minus EV. From this particular equation, we can write EF minus EV is equal to EG minus EC minus EF. Now for the first case, we will be having EFP1 minus EV equal to band gap energy EG minus EC minus EFP1. Similarly, for the second case, we have now we will put the value of these two equations in this particular equation, and after that we will get EG will cancel out, which will give us EC minus EFP2 equal to EC minus EFP1 plus KT ln P2 by P1. EC minus EFP2 will be equal to EC minus EFP1, which is given in the question to be equal to 200 milli electron volt plus 26 milli electron volt, which is KT at room temperature, multiplied by ln P2 divided by P1, which is P2 is equal to 0.5 into 10 to the power 16 and P1 is equal to 10 to the power 16. After calculation, we will get 200 milli electron volt minus 18.02 milli electron volt. This will give the answer to be approximately equal to 181.98 milli electron volt, which is the final answer. A non-degenerate p-type semiconductor has 15% neutral dopant atoms. Its Fermi energy level is located at 0.15 electron volt above the valence band energy EV, and acceptor energy level has a degeneracy of 4. Assuming the thermal voltage to be 20 millivolt, the difference between EA and EV is. We have a direct formula according to which the hole concentration at acceptor energy level is equal to doping concentration of acceptor impurities divided by 1 plus 1 upon G, where G is the degeneracy factor multiplied by exponential EF minus EA divided by KT. PA represents neutral dopant atoms at acceptor energy level, which is also given to be 15%. Therefore, PA will be equal to 0.15 Na. Degeneracy factor is given to be 4. By solving the equation, we get the value of EF minus EA to be equal to KT ln 68 by 3, and after calculating we will get the value to be around 0.062 electron volt. Now it is also given that EF minus EV is equal to 0.15 electron volt. We can also write this equation like EF minus EA plus EA minus EV is equal to 0.15 electron volt. EF minus EA we just found out to be equal to 0.062 electron volt plus EA minus EV is equal to 0.15 electron volt. It gives EA minus EV to be approximately equal to 0.087 electron volt. This is the final answer. Consider silicon with the intrinsic carrier concentration equal to 1.5 into 10 raised to the power 10. and energy band diagram as shown at room temperature. What will be the concentration of electron at 400 Kelvin if at room temperature effective mass of hole and electron is given? We have to assume that AF does not vary with temperature and the shrinkage of band gap energy happens in a manner such that the mean of conduction band energy and valence band energy remains constant. At room temperature, the energy band diagram and intrinsic carrier concentration is provided. We will first find the value of under root Nc into Nv. From the diagram, we can find the value of band gap energy to be equal to 1.48 minus 0.36, which is 1.12 electron volt divided by 2 kT, which is 0.026. The value of under root Nc into Nv comes out to be around 3.39 into 10 to the power 19 divided by centimeter cube. You have to keep in mind that Nc and Nv are not constant and depends upon the temperature. So this particular value of 3.39 into 10 to the power 19 is equal to under root Nc into Nv only at 300 Kelvin. You also know that the formula for Nc is equal to 2 into 2 pi mp multiplied by kT divided by h square raised to the power 3 by 2. And according to this, you can say that effective density of states in conduction band is directly proportional to temperature raised to the power 3 by 2, and also effective density of states in conduction band is proportional to effective mass of electron raised to the power 3 by 2. But there is no such statement in which it is said that effective mass is varying with temperature. So we will assume that effective mass of hole and electron is not varying with temperature. Similarly, you can also write for Nv. Now we are supposed to find the concentration of free electron at temperature 400 Kelvin, and we have a formula. N naught is equal to intrinsic carrier concentration into exponential EF minus EFI divided by KT, which can also be written as under root Nc into Nv exponential minus Eg by 2 kT exponential EF minus EFI divided by KT. Now, as you know already that EFI, which is intrinsic Fermi energy level, changes with temperature, and we have a formula which is equal to EC plus EV by 2 plus 3 upon 4 kT into natural logarithm of effective mass of hole divided by effective mass of electron. It is also provided that as the temperature increases, the band gap energy will also reduce, but it happens in such a manner that EC plus EV remains constant. So, intrinsic Fermi energy level at 400 Kelvin will be equal to 1.48 plus 0.36 divided by 2 plus 3/4 into 0.026 divided by 300 multiplied by 400 into natural logarithm of 1.08 m naught divided by 0.56 m naught. After calculation, intrinsic Fermi energy level will come out to be around 0.937 electron volt. Similarly, we have the formula for bandgap energy for silicon, which is 1.21 minus 3.6 into 10 to the power minus 4 multiplied by temperature in Kelvin. And bandgap energy at 400 Kelvin will be equal to after calculation, we will get the bandgap energy at 400 Kelvin to be equal to 1.066 electron volt. Now we will put all these values in the free electron concentration. And as we have already discussed that value of Nv and Nc depends upon the temperature. So Nc into Nv, and we have to multiply it by 400 divided by 300 raised to the power 3/2. We know that Nc is directly proportional to temperature raised to the power 3/2. One expression will come from the Nc and one will come from the Nv. This 300 is divided as we know the value of Nc at 300 Kelvin, and 400 is multiplied because we need to find the value of Nc at 400 Kelvin. We have already solved similar questions in which we have to find the value of Nc at different temperature and are provided with the value of Nc at some other temperature. After calculating the whole expression in the exponential, we will get approximately equal to 6.63 multiplied by 10 to the power minus 5. The free electron concentration after calculation comes out to be around 3.46 multiplied by 10 to the power 15 per centimeter cube. In the last question, we found the value of under root Nc into Nv to be approximately equal to 3.39 into 10 raised to the power 19. And we also discussed that Nc is directly proportional to temperature raised to the power 3/2. Also, Nc is directly proportional to effective mass of electron raised to the power 3/2. Similarly, for Nv we can write Nv is directly proportional to temperature raised to the power 3/2, and Nv is also proportional to effective mass of hole raised to the power 3/2. Since I have taught you only one relation of dependence of effective mass with temperature, which is Heisel relation, then we will be applying the same here also. And as per the Heisel relation, effective mass of electron at 400 Kelvin will be equal to effective mass of electron at 300 Kelvin multiplied by band gap energy at 300 Kelvin divided by band gap energy at 400 Kelvin raised to the power 4 by 3. Similar expression can be written for effective mass of hole. We are supposed to find the value of free electron concentration N naught, which is equal to Ni exponential EF minus EFi divided by kT. And as we have discussed in the last question also, that this expression can be expanded into this expression. Now you know that band gap energy does not depend upon the effective mass, and it is also provided that EF remains constant, but we have intrinsic Fermi energy level EFi which do depend upon the effective mass. Intrinsic Fermi energy level is given as EC plus EB by 2 plus 3 upon 4 kT into natural logarithm of effective mass of hole divided by effective mass of electron. In the last question, we have assumed that effective mass is independent of temperature, but here we have to consider effective mass to be dependent upon temperature. Now look carefully. We have to find the value of effective mass of hole divided by effective mass of electron both at 400 Kelvin. And as we have just found the equations above, effective mass of hole at 400 Kelvin can be written as effective mass of hole at 300 Kelvin multiplied by band gap energy at 300 Kelvin divided by band gap energy at 400 Kelvin raised to the power 4 by 3. Similar expression can also be written for effective mass of free electron. Now you can see that this expression will cancel. It means the logarithmic expression has not changed, meaning that the intrinsic Fermi energy level will remain same even though it depends upon the effective mass. So we can write free electron concentration as I hope you can understand that this factor comes from the temperature dependency, and this factor comes from the fact that NC is actually dependent upon the effective mass raised to the power 3 by 2. You should keep in mind that the value of under root NC into NV which we found was valid at 300 Kelvin only. If the temperature changes, then we have to introduce these terms also. In the last question, we have already calculated the value of this expression, which came out to be 3.46 into 10 to the power 15 per centimeter cube, and we have to multiply it with band gap energy at 300 Kelvin, which is provided 1.12 electron volt, divided by energy band gap at 400 Kelvin, which we have already calculated in the last question, equal to 1.066 electron volt raised to the power 4 by 3. After calculating it, the value of free electron concentration will come out to be around 3.69 into 10 raised to the power 15 per centimeter cube. This will be the final answer. If you find any error, then type it in the comment section.